Okay, good morning everybody. I hope you are all fine. The slides and the handouts are over there, so if you haven't got it yet, just please feel free to pick it up. And I think we're ready to go. Okay, so what we're going to do today is recap optimization, because more or less you've already done plenty of calculations. But I appreciate that it can be a little bit overwhelming for especially people who haven't done it before, because there's a lot of different steps and a lot of different things that you need to remember. So I'm going to take it slow today again. And I'm going to start with higher order derivatives, just so we can do a little bit into the move. And then spend time on stationary points, spend time on points of inflection and optimization, and then go through optimization problems, the whole process. And then I try to do an economical example as the last question. So similar questions to the worksheets. I think it's worksheet 2 or worksheet 3, I keep forgetting. But different examples, so you have an extra opportunity to practice. Okay, before we go into there, if you do want to do more practice than what's just on the worksheets, where you can get calculations from? Where can you get extra practice questions from? Textbooks. So one of them is very good, is the Jacques. And where else? Online. Okay, if you found a good website, please let me know, so I can let everyone else know. I don't think Khan Academy is high enough for this kind of work that you're doing here. That one there, yeah. Do you mind if I just show it up to everyone? Okay. So there is this book. It's also, I believe, on the recommended list. This is nothing else but practice questions. Okay, so question, solution, question, solution. So if you feel like that the questions that you've done in a class are not enough, you need a little bit more just to get yourself into the groove, because it's something that you have to do very easily and quickly, then look at those questions. And that will really help you to come up to speed. Okay. So higher order derivatives are nothing overly complicated. It's basically just start to do the differentiation over and over again. So you do it again and again. The first order derivative, you can use the prime notation. So f1 prime means the first order derivative. When you have got 2 is the second, then we've got 3 is the third. Now we often use numbers in brackets to say that this is a higher order derivative. Why you think we use brackets and not just the numbers? Yes. If you don't put it into bracket, you might mistake it for f to the third power. Okay? So that's why this bracket notation has been invented, to make sure that it's different from the power notation. I am assuming that by now you know every single one of the differentiation rules, and you know how to differentiate every single different type of function. If you don't, then there is a table of differentiation, or the rules, up on Moodle under Mathematics Support Resources. So you probably want to have a look at there, print it out, save it, and put it on your wall, on your kitchen cabinet, or in your fridge, just so you see it all the time and it goes into your memory. But the best way to do it is to do practice, practice, practice. So there's this function. So x to the 4 plus 10 times root of x, and we need to differentiate it. Okay, so what will be the first order derivative? This is a sum of two functions, which is quite handy because we can differentiate them term by term. How do you differentiate a root function? What is the rule for differentiating a root?
You would need to change it to a power.
Exactly. There is no rule for differentiating a root, because a root can be rewritten as a power. So you would need to manipulate this function first And what power will be the square root? Power of half. Okay. So every time you see power of half, you really need to think about, oh, actually, that's nothing else but the root. Okay? So how do you differentiate this one now? Become a lot simpler straight away, because it's just 2 power rules. Okay, so this will be 4x cubed plus 10 times a half x to the minus half. And if I cancel down the fraction, this will be 4x cubed plus 5x to the minus half. Second order derivative. Morning. Slides are on there. Second order derivative. 4x cubed derivative will be and what will happen to this one? Actually, can we do it all in one go? So I'm going to need to bring the power down. So I will need to multiply minus half and 5 together. That's going to give me minus 5 over 2. And what will be the power of x? Minus 3 over 2. Okay, and the last one, the third derivative. I've got a negative fraction here, and I need to bring a negative fraction down, so that's going to give me positive. And what will be that fraction exactly? And what's the power? Okay, so almost mechanical. You sort of get into the habit of doing it, and it becomes quite easy and quick. Okay, so what can you tell me? What do you notice when you see if I have got a power that is a whole number? What's the difference to that if I have a power which is a fraction? If I was to differentiate this once more, what would happen to this? This term, what would happen to that term? X would disappear. I would just end up with 24. So if I've got a whole number power, positive whole number power, and I keep differentiating the function, then at some point I'm going to end up with a constant. How about if I started with a fraction? Because I'm only lowering the power by 1, that's never going to differentiate down to a constant. It's always going to stay as a function of x. And as you can see, if I started out with a negative power, that negative power just going to keep going down and down and down. So that's, again, it's not one of those that would become a constant. So if you have got a positive whole number power, there is a point when that will become a constant. But if there's anything else, you're always going to have an x left in the function. Any questions about this one? Okay. Can I rub the board off? Okay, so the next one more that we need to sort of go through this higher order derivatives. This function, oops, not plus, minus e to the 2x cubed. Okay, now this is, again, a difference of two functions. So thankfully, I will be able to differentiate it term by term. But What do I know about each of these functions? ln x squared, what kind of function is this? A composite function. So what rule do I need to use?
Chain rule.
The chain rule. Okay, am I just being too obvious and you don't want to talk? Okay, shall we just get on with it? Okay, so what's the derivative of this one then? 1 over x squared, because you need to differentiate it according to the log rule, and then you need to multiply it with the derivative of x squared, which is 2x. Okay? And then this one, again, e's derivative is itself, e to the 2x cubed, and then I need to multiply that with the derivative of the inside function, which is the 2x cubed, which will be 6x squared. Okay? So tidy up. X I can cancel out, so I got 2 over x minus, I can bring this to the front so I don't mix up powers and x's. Okay, now I need to differentiate it again, but in this format I might not see what this function is, so I need to rewrite this as a power, and anytime when your variable is down, that is a negative power. So this is 2 times x to the minus 1 minus 6x squared e times 2x cubed. Second order derivative. What will be the first term? And what rule do I need to use for the second? What rules do I need to use for the second? I've got 6x squared times e to the 2x cubed. So this is a product of two functions, and unfortunately the second is a chain. So I need to use the product and the chain rule at the same time. So the product rule tells me that differentiate one multiplied by the other plus. So I'm going to keep a negative sign out, and I keep a bracket, so I make sure I don't mess up the rule. So this derivative is 12x, and I just multiply it with the second term. Plus, I leave the first term in the product and differentiate it with the second term. But that's exactly what we ended up in here, because that's what we started with. So that's just, again, 6x squared times e to the 2x cubed. Okay, so minus 2x to the minus 2 is a negative, so I'm going to bring that out. And so negative positive makes negative. 6x squared times 6x squared makes 36x to the 4 e to the 2x cubed. Okay, so we started with a relatively simple function, and then we ended up with a horrible looking, very long function. So this is a perfect example showing you that as soon as you've got exponential functions which are composite, differentiating them again and again is going to give you a lot more complex function. And imagine if you had to solve this. If it was an optimization problem, you had to solve this, set it equal to 0. That's a horrible equation to solve. And then on top of that, you would have to come back into here and substitute back into it a lot of places that you can go wrong. So that's why you're going to learn something called the logarithmic differentiation. So these functions, you can deal with them in a slightly different way, which makes the whole process easier.
So you call it a composite what?
Composite function. It's just a composite function of e and something else. So function of a function there. So they become a little bit difficult to deal with. But unfortunately, a lot of processes follows exponential rules. Okay? Any questions? Can I wrap the board off then? I'm going to try to open that window a little bit more because I am absolutely boiling. And the worst thing that can happen in a mathematics class is that the room gets too hot and everybody falls asleep. Okay. So, optimization. To understand optimization, first we need to know about stationary points. So stationary points are the points where a differentiable function, first derivative have been equal to 0 at that particular point. Why do you think we call them stationary points?
Where the tangent is horizontal.
Yes, and if the tangent is horizontal, that means that the function is not changing. So the function is stationary at that particular point. So very inventive name. Types of stationary points, you can have 3: minimum, maximum, point of inflection. So just by identifying where the function does not change, where it is stationary, you don't know what you found. You either found a minimum, maximum, or a stationary point of inflection. So, what is a point of inflection? Well, the mathematical definition is point of inflection is where the sign of the curvature convexity changes at this point. I don't think you have been given this formal definition, but you were told 2 conditions. Basically, the second order derivative at that point is 0, but it also changes sign at that particular point, which was a condition that the third order derivative was not 0. The 2 things are equal. So what are we talking about here? Can anybody sort of give me an example? What might be a stationary point of inflection? What does it look like? If you don't mind drawing in the air, that's fine.
Like a snake.
That's a very good example. So it could look like a snake, like your ordinary cubic function without any funky in there.
It's like, imagine you were driving a car along the line. The point of inflection would be the point, like if you started from the bottom of this line, you have to turn the wheel to the right. The point of inflection is the point where the wheel reaches straight ahead.
Yes.
Just before it goes to the left.
That's a very good example. I haven't heard about that one. That is really visual. So basically, that would be somewhere in here. Forgive my drawing. So you're driving along and then you sort of have to swirl, in a sense. Again, back to formal mathematics. If you look at before that point, doesn't matter which 2 points on the function you connect together, the line is always underneath the function. But if you go beyond this point, what happens? Whichever 2 points you pick out, doesn't matter, they are always above the function. So that's another way you can think about where is the point of inflection, or what is the point of inflection. Now this one would be a so-called stationary point of inflection, but we do have a non-stationary point of inflection. What would that look like? If I rotated it to, yes, can kind of, yeah. It's almost like if you think about your sine or cosine waves, okay, somewhere here in the middle again, what you get, if you put the lines, connect the lines together, they all are underneath the graph, and from here on they are all above the graph. So again, the curvature or the convexity changes here at this particular point. But this is not stationary anymore, because if you draw the tangent, that is not a straight line. I mean, well, that's not a constant line anymore. That is that has got some change there. The change is not 0 anymore at that particular point. Okay? So you sort of have an idea, a visual idea what's going on there, and for that, here are the formal conditions. So what you can see is that for both stationary points, the second order derivative is 0, the third order derivative is non-zero for both of them. But for the stationary, the first order derivative is also 0, while for the non-stationary, the first order derivative is not 0. So that's what distinguishes between the two types of stationary points. So the common conditions, second is 0, third isn't. But then depending on if the first is or isn't 0, we found the stationary or non-stationary. A lot of conditions that you actually have to learn. Okay? So the optimization, what's the whole point of the optimization? Finding minimums and maximums. So, as we said, the stationary points are where the derivatives are 0. So those are all these 3 points. Unfortunately, this one is like the fly in the soup, because that's giving me a point of possibility, but turns out nothing useful, because it's neither minimum nor maximum. So I will have to be able to distinguish between these 3 types of stationary points, and for that I've got the second order condition. And the second order condition is basically, depending on if the second order derivative at that particular point is positive or negative, I found a minimum or a maximum. Okay? And this is a kind of short summary of the algorithm that you have to go through while you're doing the optimization problems. So first of all, you do the first order derivative, that's the first order condition, and you set that equal to 0 and solve for x to identify the possibilities of minimum, maximum, and point of inflection. No worries. Slides are there. Then you find the second order derivative, and you substitute back every one of those values that you found previously and check if either of them minimum, maximum, or point of inflection. Now, if the second order derivative is 0 at this specific point, I may have ended up with a point of inflection, so I need to go for the second condition for stationary points. Third order derivative at this particular point where the second order derivative was 0 is not 0. I have found a point of inflection, and this will definitely be a stationary point of inflection because I derived it from the condition where the first order was 0. Now what happens if it's still 0? If the third order derivative is still 0 at this specific point? I need to go for the so-called AND test, because the function is being difficult, not really giving up its secrets, so I need to test it a bit more. The AND test is simply, I keep differentiating until I end up with something that is non-zero. And depending on if the power is even or odd, I either found extreme points, minimums, maximums, or a point of inflection. Okay? Now, how can I check for non-stationary point of inflections? Because so far I started from the first order condition, and with the first order condition I can only identify the stationary point of inflections. So how can I check for non-stationary point of inflection?
Is that a second derivative to 0?
Yes. So you need to check. I can't reach. So you need to check where the second order derivative is 0. Will that give you any new points? And if that does, I need to check if the third order derivative is 0 or not at that particular point. If the third order derivative is not 0 there, which is most likely the case, then I found the non-stationary point of inflection. Okay, so can anybody count how many different things we need to keep in mind? You won't remember it unless you did boringly many amount of examples. This is something that only comes with practice. Okay? And don't forget, anything new, you're going to make mistakes at the beginning. But mistakes are learning opportunities. So instead of getting frustrated, welcome them, because if you already know something, you're not going to make mistakes. If you don't know something, you're definitely going to be making mistakes, okay? Don't be afraid of mistakes. Right, so the general question, here is your average function, or maybe not average function. And we need to find the minimum, maximum, points and values. Okay, so remind me by the end that we still need to check the values. I usually forget. And does this function have a point of inflection? First step first, what do we need to start with? First order condition. The first order derivative have to be equal to 0. Right? That function is not very friendly. I need to differentiate it though. So what do I need to use here? Which rules again? Product and the chain rule, unfortunately. Your teacher is very nasty, giving you horrible examples. Okay? So differentiate the first term. X plus 5's derivative is thankfully just 1. I need to multiply with the second term, plus keep the first term and multiply it with the second term's derivative. That's a chain function. So first I need to differentiate following the power rule. So bring the power down and lower the power by 1. And then I need to multiply it with the derivative of the inside function, which is x minus 4. But luckily, that derivative is just 1. Okay? Play around with this one a little bit. So what I've got is x minus 4 cubed plus 3 times x plus 5 times x minus 4 squared. And this one, I have to set it equal to 0. That's a cubic. Okay, and we don't have a simple formula to solve cubic equations, so we need to think around it. Cubic equations usually can only be solved easily if they can factor it out. So can we factor out something in here? X minus 4 squared can be factored out. Okay, because this is x minus 4 to the cubed, so I can think about that as x minus 4 squared times x minus 4. So that means that from this term, x minus 4 left behind, and in the second long term, I take out the last bit, so what's left is the plus 3 times x plus 5. Now that's a little bit friendlier, especially if you have got some experience with maths, but this one here is still quite a jungle. Let's again break out the brackets and make it simpler. Well, that's just x minus 4 plus 3x plus 15. And follow my algebra because I do mess up sometimes. So what's inside this bracket now? 4x plus 11. And that's a lot easier equation to solve than this would be. Because just by looking at it, that horrifies people. This one is not too bad. So I've got a product here. When is a product equal to 0? What do you have to multiply together to get 0? 0, exactly. So either one term or the other term, or occasionally both terms have to be equal to 0. So that tells me that x minus 4 squared has to be 0, or 4x plus 11 has to be equal to 0. Now, the only number that if I square give me 0 is 0, so that means that x minus 4 has to be 0. And that gives me the nice easy point x equals 4. The other possibility, 4x plus 11 equals 0. So 4x equals minus 11. So x equals minus 11 over 4. And I hope you have got your calculator, not like me. I totally forgot to bring it down, because for these kind of calculations, we're probably going to need them. So I'm going to need some space, so I'm going to just copy the 2 points that I found, x equals 4 and x equals minus 11 over 4, which is also 3 point something. No, 2.75. Depending on which form you prefer. So I identified the stationary points. What do I need to do next? And that was a stupid mistake, because I don't know now what was the first order derivative. So can somebody dictate me what was the first order derivative?
X minus 4 plus x plus 5 in brackets. Cube.
3.
Oh, 3, sorry. Then times x minus 4 squared.
Okay. Right. So that was the first order derivative. Now we need to check for the second order condition to see if either of those points minimums, maximums, or point of inflections.
Is it not better if you use the x minus 4 squared, 4x plus 11?
Yes, we could. What was it? 4x plus 11. But that's basically the same function.
Which one better is?
Which one do you think is better? Which one? It's personal preference. I mean, okay, if you look at the first one, what would you need to do there? You would need to use the chain rule here, and you would need to use the product and chain here. How about this one? Chain and product still. This one might be slightly simpler, because you have to use the product rule once. You don't have to have, you're not going to end up with so many different terms. But really depends on your personal preference, because the final answer should be the same. The only difference is there, where are you going to make the mistake? Okay, let's go with this one. That's probably, for my taste, that looks a little bit simpler. So the derivative of this is 2 times, oops, two times x minus 4. Now the power lowered by 1 will give me power of 1, so I don't write that out. And I need to multiply it by the inside derivative, which is 1, so that's not going to change, times 4x plus 11, plus, keep this one, and then multiply it with the derivative of the square bracket. And what's the derivative of the square bracket? 4. That was actually not too painful. So what I've got here is 2 times x minus 4, 4x plus 11, plus 4 times x minus 4 squared. So that's the general function for the second derivative. And now I need to check for those 2 points. So x equals 4. The second order derivative at this point is going to be what? This term so this term is what? 0. And this term is 0 again. So what I got here, both of them are 0. Okay, because 0 times whatever is 0, 4 times 0 is 0, so the sum is 0. So it's a possible point of inflection. So what do I need to do for the possible point of inflection? How can I decide if it's point of inflection or not? The third order derivative. Okay? That means I need to differentiate this one. Now, these are two linear functions multiplied together. I'm quite reluctant to use the product rule for these ones. But if you kind of prefer the product rule to algebra, then go for the product rule. If you're not, we can just multiply the brackets out and then see if we end up with something simpler. So that's what I'm going to do. So this is x times 4x is 4x squared times 2 is 8x squared. X times 11 is 11x times 2 is 22x. Minus 4 times 4x is minus 16x times 2 is minus 32x. Minus 4 times 11 is minus 44 times 2 is minus 88. And I'm probably going to break up this bracket too, because I know already that I'm going to have to check for point of inflection. So the simpler my second derivative is, the easier it is for me to solve. So, plus the square of a difference is the square of the first, double of the two terms multiple, negative, plus the square of the second term. It's, I don't know how many of you have been taught in algebra class, a minus b squared equals a squared minus 2ab plus b squared. That's what I'm going to use in here. So x is squared is x squared times 4 is 4x squared. The double of x and 8, x and minus 4 is minus 8. Minus 8 times 4. Help someone out. Minus 8, is it minus 32? I never trust my mental algebra. And the square of 4 is 16. And 4 times 16, I definitely can't do that in my head. 64. Okay? Now, what do I have? This is a squared term. There's no more squared terms, so I've got 12x squared. The x's are 22 minus 32 gives me minus 10. Minus another 32. Minus 42x. And I've got plus 64 and minus 88. And please help me with a calculator. Because you can use it, so I don't have to go through that. What is that minus? 24. Okay. Now, much simpler than this one. Took us a bit of effort, but it's a lot simpler. And now I can differentiate that in no time. So the third order derivative will be 24x minus 42. And what I need to check is what is this derivative equal to at 4. So 24 times 4 minus 42. That is 96. And I don't know what exactly 96 minus 42 is, but what I know for sure that it's definitely not 0. So, what does this last bit tell me about the x equals 4 point? What kind of point of inflection? Stationary point of inflection. Because This is a point where I got from the first order condition. So it cannot be a non-stationary, it has to be a stationary because the first order derivative here is 0. Okay, so that is a stationary point of inflection. Now that was the first point that I identified from the first order condition. Now I need to go back for the second point. And just in case I'm going to need it, I'll just write it down there. So the second point I need to check and see what it is the x equals minus 2.75. It doesn't matter if you use the fraction or the decimal equivalent for this particular one because it's a normal decimal, it's not an infinite decimal. If it was 1/3, then you would need to use the fraction equivalent because obviously once you put the decimal equivalent of 1/3 down, you do some rounding error somewhere. So the second order derivative at minus 2.75 is equal to, and because we've got that nice and simple version here, or maybe we can see it easier from this one actually, or maybe not. Okay, which one should we plug into? This one or that one? Okay, let's go for this one then. So 12 times minus 2.75 squared minus 42 times minus 2.75 minus 24. Anybody with a calculator? Nope, that's wrong.
182. Can't be wrong.
Could be, because if you think about this one, okay, so what was that, 100?
182.25.
Okay, that is positive. So what have we found? Minimum. Okay, so minimum at x equals minus 2.75. So that one is a minimum. Okay. Does this function have a point of inflection? It does have a stationary point of inflection. Question is, does it have a non-stationary point of inflection? How would I do that? Non-stationary point of inflection.
Check the points that the second derivative is equal to 0.
Yes.
And check if any of those you didn't already find with your first derivative.
Exactly. And one of them has to be the one that we already found. So we need to pick up the second order derivative, which is this one. And we have to set that equal to 0. Okay? So 12x squared minus 42x minus 24 has to be equal to 0. This is a simple quadratic. The quickest and easiest way to solve any quadratics is to use the formula. But one thing I spot about this quadratic is that every single term is even. So I can cancel down the whole quadratic by 2. That would give me 6x squared minus 21x minus 12 equals 0. The only reason why I'm doing it, because in this case I will end up with smaller numbers in the formula, and that is easier to solve. So, anybody remembers the quadratic formula? Minus b plus minus square root of b squared minus 4ac over 2a. What is a, b, and c in this case? Those are the coefficients of the different terms. A is the coefficient of the quadratic term, b is the coefficient of the linear term, and c is the constant term. Okay? So this will be minus b, so minus 21 is 21, minus 21 square, minus 4 times 6 times minus 12 over 2 times 6. Now, if you know very well how to use your scientific calculator, you can plug the formula in one go, first using the plus, and then going back with the arrow buttons, and then just deleting the plus and making it a minus. And that's why I really wish I brought that down my calculator. Okay, so the steps for this to do is, first of all, it's a fraction, so you would need to type the fraction button. And then on top of the fraction, you need to type in 21 plus, then you press the square root button. Under the square root button, you just put this one in. Then you press the arrow button, probably twice, because first you need to come out from the square root, then you need to go down. And the two roots should be, what do we expect one of the roots to be? What are we finding here? What are we looking for in here? We're looking for the points of inflections. We already identified one of them, x equals 4, so we're expecting one of the roots to be x equals 4. And if you do the calculations, then yes, one of the roots is x equals 4. And if you do the other, that gives you x equals minus 0.5. So that's our already known stationary point of inflection. So this one is a possible non-stationary point of inflection. But to be sure, slides are on the table here. But to be sure, what do we need to do? Look at if the third order derivative at minus 0.5 is 0 or not. So the third order derivative at minus 0.5 is equal to 24 times minus 0.5 minus 42. Now, without actually working exactly out the value, can I tell if it's equals to 0 or not? Is it going to be 0? It doesn't matter what the value is, I know it's definitely not 0. If you want to be precise and exact, you can again just put that into the calculator, give an exact value, but that is still not 0. So what have we found? Non-stationary point of inflection at x equals minus 0.5. Okay? And the function given up all its secrets, so we can do another example. That looks just lovely, isn't it? Is that all right if I wrap the board off? Okay. Find the minimum, maximum, and point of inflection. Oh, we haven't finished with the previous one. Because you didn't remind me for what I told you I'm going to forget. What have I forgotten? The values. Okay. Now, what was the minimum point? X equals minus 2.75. Is that correct? Okay. Now, point of inflections, the values for point of inflections doesn't really matter. What we're interested in is the minimum and maximum values. Okay, we don't have any maximum in this particular function. We only have got a minimum. By the way, is that minimum a global or a local minimum that we found? Local. A cubic function, what do you know about the cubic function's general form? Sort of coming from infinity, going to infinity, either this way or this way, depending on if you have got positive or negative for the cubic term. This one was positive, so it's one of these functions going up. But it has got this sort of kind of quirk in there. Okay. So sorry, it's a. I'm talking rubbish. What kind of function is this? What power function is this? Fourth power. Okay. So this one of those simple fourth power functions. It looks more or less like a quadratic, but a lot squashed together. So it's not one of those quadratic when you have got the thing in. It's just a simple one. And it was so mathematical.
But with the points of inflection?
Yes.
How did that fit in? How would that fit into the
Actually that's a very good question. They don't. So I'm wrong. Because the points of inflection don't fit into there. So there must be some quirk in that function, some wiggle somewhere, but that wiggle probably is something like this. Okay. Okay. That's the minimum. And how do we find the minimum value? Plug it into the simple function. So we just need to find the value of this, which is minus 2.75 plus 5 times minus 2.75 minus 4 cubed. And again, calculator work, a little bit boring. If you have the calculator and if you're very quick at working with it, it will save a lot of time for you in the exam. So you probably want to start getting used to it. Okay? I mean, the exact value doesn't really matter. It's just what's important is that you don't forget about this point if you have been asked. Okay? I leave it as a calculator exercise for you people. Right, let's get back to this lovely looking function. So the second example, so find the minimum maximum point of inflection of the following function, if any. What are we going to do? First, to the condition, we need to differentiate the function. What kind of function is this? Quotient. So we need to use the quotient rule. And I am not 100% sure if I'm going to do it the way that Tony does, but the result is exactly the same. So the way I do it is differentiate the top, which is 3, times the bottom, minus, leave the top, multiply it with the derivative of the bottom, which is minus 3, and all over the numerator's square. Yeah?
You could just multiply it by 1 minus 3x, couldn't you, and then use the product?
I could do 1 minus 3x to the power of minus 1. So I could rewrite this as 3x times 1 minus 3x to the negative 1 and use the product rule. That's true for every more or less true for every quotient function. If you prefer the product rule, you can just rewrite it and do it that way. But we will have to solve it anyway, so you're going to have to bring it back to the fraction form. So it doesn't make much difference. So, because this has to be equal to 0 according to our first order condition, I'm going to have to make this function a little bit nicer. So, 3 times 1 is 3. 3 times minus 3x is minus 9x. Minus 3x times minus 3 is positive 9x over 1 minus 3x squared. So that is a relatively simple 3 over 1 minus 3x squared. And what do we know? This has to be equal to 0. What's the solution to this equation? Positive number divided by something has to be equal to 0. Can I solve it? I cannot solve it because I cannot divide by 0. 3 over 0 is not defined. So this equation does not have a solution. What does it tell me? Exactly, just as simple. There are no stationary points, so this function will not have a minimum or a maximum in a sense of local minimums and maximums. Now, what does this function look like? Anybody has got some ideas? Not parabola? Hyperbola, yeah. Okay? It's this function. Okay? And it's boring, doesn't have anything. Its maximum is plus infinity, its minimum is minus infinity, and it doesn't even have these sort of interesting features. Okay? Don't worry, in the exam you're not going to get a function like this because that's just pointless because they want to test your understanding of these conditions, but you might come across something like this in real life. So just be aware of that not every function have got local minimums and maximums. Some of them just go into infinity.
Does it have non-stationary points of inflection? Is that what those
okay. What is the point of inflection where the curvature changes? Does it change curvature anywhere? Or does this change curvature anywhere? No, so it doesn't even have that. However, if you wanted to formally check, you would need to do the second order derivative, which would be again quite simple, because this one I can now rewrite minus 2, and then the second order derivative would be just minus 6 times 1 minus 3x to the minus 3 times minus 3. So that would be 18 over 1 minus 3x cubed. And again, I can't solve this equation. Same situation, because a positive number, I can't divide by anything to end up being equal 0. So again, that's why I can see algebraically why there is no point of inflections either. But the graph nice and easily gives the information away just by looking at it. Okay? That's nice and easy. Finished quick. I can't promise about this one. But you can give me the credit that at least this time I was nice. It's not a horrible one to differentiate. Oopsie. So first order condition, the first order derivative have to be equal to 0, so we can identify possibilities for minimums, maximums, and point of inflection. So the first order derivative is 6x squared minus 16x cubed. And that has to be equal to 0. So again, we ended up with a cubic function. So how are we going to try to solve it? Trying to factorize it. So what can we factorize out from these two terms? 2x squared. What's left from this term then? And what's left from this term? Again, solving it goes, if one of the terms or the other is equal to 0, that's when the multiple will be 0. So 2x squared is 0, or 3 minus 8x is 0. 2x squared will only be 0 if x squared is 0, but the only number I can square to give me 0 is x. Sorry, is 0, so x has to be 0. And this one is 3 equals 8x, so x equals 3 over 8, which is 0.375. So the 2 points I identified as stationary points is x equals 0 and x equals 0.375, or 3 over 8. We'll see later which form will be more useful. But as long as you've got the calculator, it doesn't really... Sorry. But as long as you've got the calculator, it doesn't really matter if you use the fraction or the decimal. Okay? So now we've got the possibilities. Well, we also need to identify what we found. Bless you. So second order condition, we need the second order derivative. So differentiate this one again. What we're going to end up with? 12x minus 40. Lovely, 48x squared. Okay? So, the second order derivative at 0 will be 12 times 0 minus 48 times 0 squared. So that is a big fat 0. So this is a possible point of inflection. What do I need to do? Third order derivative. So that was the second order derivative. What will be the third order derivative? 12 minus 96x. And the third order at 0 is equal to 12 minus 96 times 0, which is not 0. So what is this point? Exactly. So that was when x was 0. Should have probably wrote that down here. So when x is 0, this is what we found. Now, I need to check for the other one. So when x is 0.375,
-2.35.
2.5 or 3?
2.5.
Okay. So this is negative. What have we found? Yes, a local maximum. Okay, so this is a local maximum. Why do I know that this is not a global maximum?
Is it because it's not constant? Second.
Yes, because the second order derivative is not the same sign for each of the values of x. So if it was negative for every single x value, that would be a global maximum. If the second order derivative would be negative for every single x value, the maximum we found would be a global maximum. But because it changes sign at certain points, it is just a local maximum. And again, that's a function to the power of 4. I think it's called the quartic functions, but don't take my word on it. Unfortunately, I studied in a different language in my first degree, and sometimes maths vocabulary still trips me up. And because that's a negative in here, what kind of function do we expect? Which have a local maximum but not a global maximum. Yes, that could be, but the fourth power is kind of right. So this could be one of these kind of functions, but then again, I'm not 100% sure without being exactly able to do it, because we don't have a global max. So it has to be this way. I mean, if it was this kind of function, that is usually an odd power. The even powers are either this way or that way. But if it was this way, we would have a global max.
But we don't have a medium. Sorry. The question is, we don't have a medium.
Oh, you're absolutely right. So then, let me think about it. What could it be? Because we don't have a minimum. You know what? I need to think about that question next time. Probably the easiest if you put it into Excel and see. Or there are some function graphing websites that you can just put into it.
If you type it into Google, it actually just graphs it for you.
Oh,
Yeah, it's amazing.
There you go, technology. I haven't even tried that one, but what did it look like then if you typed it into Google?
I was going to ask something different. I still don't really understand why that's a local max. Why you know that's a local max.
Okay. You know the second order condition. Is it going to be positive or negative for every single x values along the x-axis? Can I set it equal to 0 and find a point when it's going to be 0, meaning that it's going to change sign somewhere? For those kind of functions which you end up with f double prime of 4 being equal to 2 or being equal to minus 4, those are the ones that have global minimums and maximums. Because for every single value, this is the only one that is the biggest one. But this one is not that type of function because it's going to change sign somewhere.
So even let's say if it's not going to be minus 48, it's going to be plus 48, could be or could be kind of a global maximum. If the sign is the same, like plus 12 and plus 48, yeah?
So 12x plus 48x squared. Okay?
What would it be?
That's again what you need to think about. Is it positive for every single, sorry, what are we looking for? Is it the same? Is it all positive for every single x value, or if it's all negative for every single x values? I mean, this one will be always positive, that's for sure. But depending on if x is positive or negative, I can probably find a big enough x. Can I find a big enough x? But this one would be bigger than that. Because if it's negative here, I'm only multiplying it by 12. But if it's negative here, I square it and multiply it with a much, much bigger positive number. So that's probably could be. Because then it's quadratic. We can probably answer that question when we look into, because we found those 2 points now, but what else do we need to find? See if we, no, I didn't ask that question in here, but do we have any non-stationary points of inflection? Because we did find a stationary point of inflection, but we still have a possible non-stationary point of inflection.
Or sorry, just like phrasing it like we are looking for the possible, all the possible routes, isn't it?
Yes.
Just, we have to stop by, we have to define all the potential station, maximum,
Yes.
until the very last route.
Yes. I mean, this is not going to have a minimum, because if it did have a minimum, we would have already found it here in the first order condition.
Yes.
But the only thing that we can't get from the first order condition is the non-stationary point of inflection. So first order condition, second order condition finds you minimum, maximum stationary point of inflection, but not the non-stationary. So that's why we need to check it again. So the second order condition, the second order derivative, which is 12x minus 48x squared, have to be equal to 0. That's one of the conditions for a non-stationary point of inflection. So I'm going to have to solve this. Now, this is a quadratic, but it's missing the constant term. So I can solve it without the formula, just by factorizing out. What can I factor out? And what's left behind? So again, a multiple is only 0 if one or the other terms are 0. So either 12x is equal to 0, which gives me the x equals 0. And I'm happy with that because this also have to identify the stationary points of inflections as well. But I can see that I ended up with another point, which is 0.25 or 1/4, and that is most likely my non-stationary point of inflection. So the third order derivative, is 12 minus 96x, and at 0.25 is that going to be 0? What is the quarter of 96? Is it 12? No. 48 has got a quarter equal to 12. 96 doesn't, so it's non-zero. So this is a non-stationary point of inflection.
So I graphed it out.
Mm-hmm.
It just looks like a U with a flat top, but with just like a really faint squiggle just at the top. You know?
Okay.
Like that.
Oh,
It's very subtle.
it's almost you can't almost see that.
Yeah, it almost looks like
Wow. Okay, I'm gonna stop pretending that I understand functions better than I do, because quadratics very easy to see, top or bottom, coming up or down. But as soon as they start to become a bit higher powers, they become a bit funny looking, and you can't ever predict how many terms are in them in most cases. So I still believe that it's a good idea to try to draw them if you can. Obviously, if you do practice questions at home and you have got your phone or Google close enough, because it gives you a powerful visual about the function. But now I'm getting sort of confused, because looking at that function, I should have been able to say that this is actually a global max, because that's one of those ones which is at the top, kind of thing. So the second order, okay. If you look at this one, how can we say that this is a global maximum or not? Because the function ended up looking something like almost something like the squiggle in there, but probably you can't even see that tiny little squiggle. So global maximum, meaning that this has to be negative for all possible x's. Why do you think that is true then? So this one is negative for all x.
because the second term's always bigger than the first.
Okay? If it's positive, if x is positive, I've got a relatively small positive number take away a much bigger positive number. If x is negative, I've got a relatively small negative number and I'm taking a bigger number away from it. Because remember that x squared is always going to be positive. So for both situations, I'm going to have negative solutions. Doesn't matter if it's x or positive or negative. So that's why it's actually going to be a global maximum. And ignore what I said before. I hope I haven't confused you. And these kind of questions, I don't know how much emphasis is paid on finding global or local maximums. Not much, as long as you identify the maximums. I mean, yes, go ahead.
Just to say that it's always local.
Okay, just to be on the safe side and not mock up yourself. Okay. Well, this is a perfect example why that is a wise otherwise. Okay, let's look at an economical example. Now, I have seen a few students on tutorials, and what I kind of picked up, and it's not the majority, but a few people sort of looking at these questions and don't really know where to start from or what to do with it, and then it turns out that they're not really clear on the economical terminology. Okay, so total revenue is involved. So straight away you need to know how to calculate total revenue, because you might need to use that later on somewhere. Cost functions. Cost functions, you need to know what kind of parts are in the cost functions. What is the difference between variable and fixed costs? And those sort of things. And what is the profit? How do you calculate the profit? So these ones, again, definitions and formulae that you really need to be clear about. Because otherwise you don't understand the question otherwise. And again, what's the difference between the average and the cost kind of thing. So I've got the total revenue there, and find the output level at which average variable cost is at a minimum. So what do we need to do here?
Divide everything with the variable by Q.
So I'm going to have to look at the cost function first. And I know that the average variable cost by definition is the total cost divided by the quantity. And that's what I meant by you need to know the terminology. And that is nothing else but Q cubed minus 6Q squared plus 140Q. Oops. That's it. And not the total cost, but the variable cost. Okay? So this part is the fixed cost, because it doesn't matter how many quantity you produce, that is always in there. Even if you don't produce anything, that is still a cost. And any term that has got the Q in there, that's the variable cost. So the average variable cost is just the variable cost divided by the quantity. The total, the average total cost would be the total cost divided by the quantity. And I need to divide that by Q. So I end up with Q squared minus 6Q plus 140. So I identified what my average variable cost is. But now I need to find the output level at which this is minimum. So first order condition. Where is the first derivative of my average variable cost is equal to 0. So the average variable cost's first derivative is 2Q minus 6. Nice and simple function. And that is equal to 0. So Q is equal to 3. I hope everybody sees that. Now, is this a minimum? I'm hoping so, but I can't know for sure unless I do go for the second order condition. And what's the second order derivative? 2, which is positive. So I'm happy because I did find a minimum. So the level, the output level, which the average variable cost is minimum, is 3. That was nice and easy. So that was A. The next question is the profit maximizing level of output and the maximum profit. Okay, can I rub the board off? So profit, how do you calculate the profit? And luckily I don't have to calculate anything in here because I know all the total revenue and the total cost. You just have to plug those in. 1,400 Q minus 7.5 Q squared. Take away the total cost. Now, just to be on the safe side, I'm going to put it into a bracket. Q cubed minus 6Q squared plus 140Q, and I don't know why I'm writing so high up, plus 750. Okay, have I got it right? Okay, so break up the bracket. And then look at the numbers. So I've got 400Q minus 140Q.
Did you lose the one?
Oh, yes, I did lose the one from the 4. Would have maximized the total different profit otherwise. So 1,400 minus 140 gives me 1,260. Minus 7.5 Q squared plus 6Q squared gives me minus 1.5 Q squared. And there are no cubic term, and there are no constant term other than those two. Okay? So that's the profit. How am I going to find the profit maximizing level of output? First to the condition. The first order derivative of the profit have to be equal to 0. So I need to differentiate this function. And that is 1,260 minus 3Q minus 3Q squared. That's cost constant. That has to be equal to 0. So what I end up here with is a simple quadratic, which I need to solve. I prefer the positive sign for the quadratic term, so I'm just going to rearrange the equation slightly. So 0 equals 3Q squared minus 3Q, no, plus 3Q minus 1,260. And what do I spot? I can divide the whole equation down by 3. So 0 equals, Q squared plus Q minus 1,260 divided by 3. What is that? Gives me 420. And then what I can do now, again, just use the formula, or I probably wouldn't find quick enough the factoring out in here. So I would just do the formula. So minus 1 plus minus root of 1 squared minus 4 times 1 times minus 420 over 2. And let me just try to find my answers. So I end up with Q being 20 and Q being minus 21. Now 420 unfortunately has got way too many factors in it, so that's not very easy to factor out. So quicker to do the formula. Now I ended up with Q being 20 and Q being minus 21. What can I straight away say? What about this one? Okay, quantity. quantity can't ever be negative, so that's not a route that is useful for me. It's either a minimum or a maximum or a stationary point of inflection as long as the function goes, but it's a practical example. So I'm not interested in negative levels of output because I can't ever have them. So luckily, I only need to deal with the Q equals 20. But that is my possibility for the maximum, the profit maximizing level of output, but I need to double check because I could have ended up with a minimum here. So the second order derivative is minus 3 minus 6q. And when q is 20, then this second order condition will become this. And what can I tell about this? Yes, it's negative, so I'm happy.
Would there be a global maximum even if it wasn't there?
Okay, can I find any q values which would change the sign of this one? So if q is negative, that would become positive. So this term would be bigger than minus 3 for already q equals 1. Okay, so this is probably a function that doesn't actually have, because it's a cubic. So this is one of those squiggle looking ones. No, not minus 63, minus 123. You're not paying attention to my algebra, are you? I told you that I do make these silly mistakes. Yes? Oh. But the question was, if it wasn't a real life example, what would the function look like? But yeah, that's the point, because the q can't be negative, so I can't really look into that area of the function anyway. Okay, find the profit maximizing level of output and the maximum profit. So what's the maximum profit? Because this is the profit maximizing level of output. But what's the maximum profit? So what do I need to do then? Just plug back into the original profit function, the q equals 10. Sorry, q equals 20. So 1,260 times 20 minus 1.5 times 20 squared minus 20 cubed minus 750. And if you put that into the calculator, that gives you 15,850. And we got one more question. What is the price at which the good is sold? Now, I've got two functions, but none of them have got any price in them. Well, what do I know about the total revenue? So if I know this, then how can I calculate the price? So if I got my total revenue, which is 1,400 Q minus 7.5 Q squared divided by Q, that gives me 1,400 minus 7.5 Q. Now that's still not a number, but how can I actually find out that particular number? Just plug the Q back in, what I found. Because obviously you want to sell the product at the profit maximizing price, and that comes from the profit maximizing level of output. So that is again should be 1,250. Okay? Right, now what kind of example did I not choose for optimization problems? What are the kind of problems you might have come across with when we go back to the general functions? What we did not see today? Nth test? Okay. How are you with the nth test? Okay? Anybody has got one of Tony's worksheets here? Wow, already that many. I think it's 2, isn't it? Okay, I think if I choose this function, at least I hope if I choose this function, Hmm?
1D you needed it.
1D was the, oh yeah.
Well, at least I did, maybe no one else did.
Okay. Okay, let's just go through this to be on the safe side. Okay. So first order condition, it's not f anymore, is it? The first order derivative have to be equal to 0. So y prime is a 6 times 4 times x minus 1 to the cubed times by 1, because the inside function's derivative is 1, but that's not going to make much difference. And that has to be equal to 0. So that is 2/3 times x minus 1 cubed equals 0. Now, this is only going to be 0 if x minus 1 is equal to 0. So x have to be equal to 1. Pardon?
Isn't it like 3 times?
It's just one, but this is just 1 point. Doesn't matter how many times you multiply it together, it's just 1 point. So it's just x equals 1. Because what number you need to cube to get have 0? 0 the only number you can cube. So the only point, the only stationary point we have is the x equals 1. So what kind of point is this one? Look at the second order derivative, which is 2/3 times 3 x minus 1 squared. That is 2 times x minus 1 squared. But at x equals 1, the second order derivative is 0. So that doesn't tell me anything so far. I need to go for the third order derivative. So the third order derivative is 4 times x minus 1. And if I look at the value of this at not 0, x equals 1, that is 0 again. So what do I need to do now? Go into the nth test.
Sorry, the second one, there is some question in my mind, obviously, but if it's 0, the second order condition might be not doesn't it mean something about the point of inflection?
It's a possible point of inflection. So it's a possible point of inflection, so that's why we're checking the third order. But if the third order is still 0, then we need to go into the nth test. That means differentiating until I end up with something that is a non-zero derivative at that point. So what I need to do now, I need to find the fourth order derivative. The third order derivative was 4x minus 1. So the fourth order derivative then will be 4. Now, this derivative at x equals 1 is 4 as well. That is non-zero.
So why at the fourth is it 4?
It's 4 everywhere. It's 4 everywhere, so at every single point it's going to be equal to 4. But in this case, you're not interested in every other point, you're interested in this particular point, because that is the point of interest for you. If it was still some x or something in here, I would need to substitute that for 1. But as the x gone away, once the x is not there in the function, that means that doesn't matter what x value you choose, the function is always going to be equal to that particular value. It's one of those constant functions. So at every single point, I'm going to end up with this 4 value.
Is that because at the third stage that 4's there? Is that where that 4's coming from?
Yes. The third stage was 4x minus 1, so I can write that as 4x minus 4, and if I differentiate this, I end up with 4 here.
Okay, and that's why it's 4. And if it was 8, then this would be
8.
everything would be 8. Fine.
Yeah. Okay? Now, this is the first non-zero derivative, which is the fourth non-zero derivative. So this is an even derivative when I found a non-zero derivative. And this is positive. So what have I found? Mm-hmm. Okay. What would have I found if it wasn't the fourth? What was the fifth derivative? Point of inflection. So the number of derivatives is key in here. Because it's an even derivative, I found a minimum or a maximum. But if it's an odd derivative, I found a point of inflection. Okay, any other questions? I seem to have timed myself better this time. Okay, thank you very much. If you have got any questions that you don't want to ask in front of the class, I'm still around, okay?
Yes.
And don't forget, you can always email me any of your questions or come and organize a tutorial, okay?